All right, welcome to the Chapter 7 Normal PDF Distribution chapter. Well, we'll be doing section 7.1, 7.2, and then we'll do 7.4. We'll be skipping 7.3 from this section. Now, 7.1 actually has 4 different learning objectives, so we're going to be looking at the properties of a normal distribution. It's really basic stuff, okay? We'll first look at the uniform probability distribution, and then the graph of a normal curve, and then we'll state the properties of the normal curve, and we'll explain the role of area in the normal density function. Okay, hence why we had to spend so much time in probability, because we're going to make the connection between the normal curve and a probability um, distribution. So first, let's take a look at a uniform distribution. And here's a scenario. Basically, it's imagine that a friend of yours is always late. So we're going to let the random variable x represent the time from when you're supposed to meet your friend until he shows up. Suppose your friend could be on time, which basically would be x equals 0, or up to 30 minutes late, x equals 30, with all equal intervals of time between x equals 0 and x equals 30 being equally likely. For example, your friend is just as likely to be 3 to 4 minutes late as he is to be 25 to 26 minutes late. The random variable x can be any value. um, the random variable x can be any value in the interval from 0 to 30. So that is from 0 greater than or equal to x, which is less than or equal to 30. Because any two intervals of equal length between 0 and 30 inclusive are equally likely. The random variable x is said to follow a uniform probability distribution. And so here are the properties of a uniform uh, probability um, density function. So this is actually a property of a probability density function. So we'll look at an example of uniform. So a probability density function, we sometimes call it the PDF, is an equation used to compute probabilities of continuous random variables. It must satisfy the following two properties. The total area under the graph of the equations over all possible values of the random variable must equal 1, and the height of the graph of the equations must be greater than or equal to 0 for all the possible values. And so the area, if we divide up our uniform probability distribution function from 0 to 30, if we divide it up and make the height 1/3, this area will be defined as one whole. And all the values possible are positive. And so this is an example of a PDF. And we can do problems like that. Like, for example, it says here, the area under the graph of the density function over an interval represents the probability of observing a value of the random variable in that area. So that's the connection. The area is going to equate to the probability. So here's a problem. It says refer to the situation in the previous example. What is the probability your friend will be between 10 to 20 minutes late? Well, if we were to shade in that region on the uniform graph and calculate the area of that portion, that area will be equal to the probability. And we know that the height of that rectangle is 1/30th, and the width is, the difference is there is 10. So 10 times 1/30th, which turns out to be 1/3, which is about 0.33, a 33% chance. Here's another problem. It says it is 10 a.m. There is a 20% probability your friend will arrive within the next blank minutes. So we need to calculate that. If it's 10 a.m., and we know that the probability is 20%, then we need to then figure out, okay, how much over will it be in order to get a 10% region of the graph. So they have this formula here where we say 1/30 times x is 0.2, and if we solve for x, we get 6. So every 6 minutes that passes will represent 20% in terms of probability. It's a good question. All right, so we're going to switch gears now and focus in on the most popular type of distribution, and that is the normal curve. And in mathematics, a model is an equation, a table, or a graph used to describe reality. The red curve in each distribution is kind of outlined by a red curve. That is called the normal curve, which is used to describe continuous random variables that are said to be normally distributed. And a continuous random variable is normally distributed if its relative frequency histogram has the shape of a normal curve. All right, so here we have the normal bell-shaped curve and the points at x equals mu minus sigma and mu plus sigma. That's one deviation away. It's just are properties of a normal bell-shaped curve. All right, the curvature curves in such a way that 68 or close to 70% of all the data values are within one deviation from the middle, which is the mean. There are different shapes, though. There are different normal distributions. There are some that spike up, go lower or flatter. So let's look at some of the properties of a normal density curve, though. Okay. So one of the things is that it is symmetrical. Also, therefore, since it's symmetrical, the mean, which is equal to the median, which is equal to the mode, has a single peak and it's the highest point. It has inflection points. The area under the curve is exactly 1. The area under the curve to the right equals the area of the curve to the left, which is a half. Here we have as x increases without bond, the graph approaches but never reaches the horizontal axis. As x decreases without bond, the graph approaches but never reaches the horizontal axis. The empirical rule is the 68, 95, 99.7 rule. This is that famous chart, and there's so many problems that can arise from this if you understand. Let's go back. If you understand the normal distribution, and so this is the empirical rule, which basically states 68% are within one deviation of the mean, 95% of data is within 2 deviations of the mean, and nearly all of the data values in a normal distribution are within 3 standard deviations of the mean. So once you go outside 3 deviations, it is very rare and unlikely. Like even in terms of an IQ, where in the IQ test, the mean is 100 and the deviation is 15, which basically implies 68% or close to even 70, just round it off to say 70% of people will have an IQ between 85 and 115. But if you get an IQ up to 145, you're now in the upper echelon of all people, less than a fraction of a percent. So this is what this tells us, and then this is the notation at the bottom. Mu is the mean. Mu plus little sigma is the deviation, the mean plus the deviation. So plus or minus, we're going within one deviation, meaning plus or minus both ways. And each little sector is there 34, 13 and a half, 2.35% roughly. All right, so here it says explain the role of area in the normal density function. And there's quite a lot of ways to calculate. Let's get it right here. There's quite a lot of ways to calculate the area. Sometimes we can even use tables to do it. So here we have this frequency distribution table, and it represents the heights of pediatricians' 3-year-old female patients. The raw data indicate that the mean height of the patients is mu 38.72 with a standard deviation of 3.17. Here it says draw a relative frequency histogram of the data and comment on the shape of the distribution. And clearly this is a normal bell-shaped distribution. Now if we superpose the shape of that, we're actually going to get that normal bell-shaped curve. Now, we don't really use this function much, but it turns out that that nice, smooth, bell-shaped curve actually can be described by this complicated function. And so yeah, we can actually locate certain points and certain values of x. And we can get the height of the curve, which would be a percentage. There's another way to go. We will not be, it even says it at the bottom here that it's just, we're just showing you, they're just showing you that normal bell-shaped curve is real. It's not just theoretical. There is an equation that represents that. All right, so we're going to focus in on the area under the normal curve because we know that it is a probability density function as well. I mean, it is a model of a probability distribution. All the values are positive and the sum of all of them equals 1. So the area under the curve will be equal to the probability. Here they say it. The proportion of the population within characteristics described by the interval of values, or the probability that a randomly selected individual from the population will have characteristic described by the interval of values. So here we have a question. It says the serum total cholesterol for males 20 to 29 years old is approximately normally distributed with a mean of 180 and a standard deviation of 36.2. Draw a normal curve with the parameters labeled. That's good enough. And now here's a question. It says an individual with total cholesterol greater than 200 is considered to have a high cholesterol. Shade the region under the normal curve to the right of 200. All right. Now suppose that the area under the curve to the right of x equals 200 is 0.2903. We're going to learn how to actually figure it out. Provide two interpretations of this result. And basically what we can say is that the proportion of 20 to 29-year-old males will have cholesterol is 0.29, and we can also interpret it as the probability that a randomly selected 20 to 29-year-old male has high cholesterol. So now we're going to do 7.2. It looks like our screen was a little off-centered, so it has just been fixed. Let's look at 7.2 now. Applications of the normal distribution, and this is really the meat of the chapter. This is the section that you must master. All right, this is where this is the section that makes chapter 7 really. And most of the problems on the quiz and the final will come from 7.2. So you do want to spend some time and really understand it, and you want to be able to do it in multiple ways as well. You want to be able to use a table, you want to be able to use technology, and you want to be able to do it using multiple different streams of technology. So you're going to find and interpret the area under the normal curve and find the value of a normal random variable. So that's kind of the opposite. So first, find and interpret the area under a normal curve. Now, there's a lot of different ways of going about doing this. If you're using the tables, then you will have to standardize your score because the tables scores are standardized, and so that's how you're able to locate your score as it pertains to your problem by standardizing it. And the formula to standardize your score is simply to take your x value, you subtract the mean from it, and divide by the standard deviation, and then that will be called your z-score. So the mean should be 0. That's the thing. That the mean is 0. Now, and the standard deviation is 1 and a standard normal distribution. So if a normal random variable x has a mean different from 0 or a standard deviation different from 1, x can be transformed into the standard normal random variable whose mean is 0 and standard deviation is 1. And so here's your standard normal curve. And table V gives the area under the standard normal curve for the values to the left. All right, so here's a question. It says IQ scores can be modeled by a normal distribution with mean 100 and standard deviation 15. An individual whose IQ is 120 is 1.33 standard deviations above the mean. So 120 is the score, 1.33 is the standardized score, that's the z-score. And that is the amount of deviations it is away from the mean. And once we have that, we can go to 1.33. So first we go to 1.3, and then we go to 300th column. And what we see is that the area to the left from 1.3 all the way to the left is already 90%, 0.9082. So the area to the left is 0.9802, and there's a technique to be able to get the area to the right. So that's why they don't give you the area to the right. You have to find it on your own. But if you have the area to the left, you can get the area to the right by subtracting 1. And that's what they did. So the remaining portion is therefore 0.0918. That's the proportion. That's the probability of having a score higher than 120. So here they're saying again the heights of 3-year-old girls is normally distributed with a mean of 38 and standard deviation 3.17. Use the normal model to determine the proportion of 3-year-old females that have a height less than 35. It's always a good idea to draw out the normal and then shade the desired area. And then you will have to convert your score, which is 35, convert that to a z-score, and that's negative 1.17. And now what we'll do is calculate the proportion of that from negative 1.17 all the way to the left. And we can look it up in the table. Negative 1.17 corresponds to 0.1210. That's the area under the curve. That's the proportion of the area under the curve. And now we answer the question. Now, there's probably going to be, well, wait a minute, do I have to always do the table? No, there's other technology that can do this problem as well. Minitab will give it, and we'll also show how to give it using technology as well, using the TI-84. Here's how one would do it out by hand. You still have to look up your table. Alright, so now they show you actually how you can use it using technology. So let's do that as well. Let's demonstrate this. So I'm going to start my calculator here. And what they want, let's go back to the original problem. They want us to find the probability that a female is between 35 to 40. Alright, so we basically need the lower bound and the upper bound. We'll need the mean, and we'll need the standard deviation. And so we go to second distribute, and it's number 2, normal CDF. And we put in the lower bound and the upper bound. 35, 40, the mean, which looks like we'll have to go back and get the mean. Uh, 38.72 3.17 hit paste. All right, and so that's what we got, 0.5365. That was really easy to do. That is the method that we do. That's how we do it. And there it is too. They got 0.5344. Well, we got 0.5365, and our answer is more precise. They got it using a table. So there's different types. I mean, the calculator will do this one as well. We'll just have to put in a very small negative number for our lower bound. So we'll still have to do lower bound, upper bound, and then the mean and the deviation, and it will give us that area. Alright, normal CDF is the main function to use. Normal CDF will get you through this section. No problem. Alright, looks like StatCrunch will do it as well. You would put in the mean, standard deviation, and what area you're trying to find. And it will spit it out. It will give you the answer. In this case, it's 1 exactly. So the entire chart. Let's look at the second objective now. So you're going to find the value of a normal random variable. And this time, they basically give us the area, or the percentile, and we have to find the x that corresponds to it. So it's kind of like going in reverse. And in order to do this, we need to have the area to the left. And now the area to the left of 20% is the same as the upper 80%. So we have to understand that under the normal curve is a full 100. So x separates the lower 20 from the top 80. One thing you can do is find the proportion in the table and see which one that corresponds to. So the table's still pretty helpful for this. But in technology, we don't even bother with that. We can use technology, and there's a function called inverse norm. So it's underneath normal CDF. If you go back to second distribute, you go to inverse norm, and we put in the area. In our case, the area is 0.2. The mean is 38.72, and our standard deviation is 3.17. And we're by default it's area to the left. And what we get is a score of 36.05. And that's exactly what they got. So that's 36.05 is right there. It represents the number that separates 20%, bottom 20% from the top 80%. All right, what score separates the middle 90% of test takers from the bottom and top 5%? And remember, the middle 90% implies that there's 5% on each tell. So it's in other words, find the 5th and 95th percentiles. So this is pictorially, this is what it would look like. And we would go to 5 and 95. But since the graph is symmetrical, what we get on one side is probably what we're going to get on the other side as well. Well, inverse norm will actually do this for us, so that's the key behind inverse norm. So these are just all examples of what's happening. And now there's this little notation that says that z sub alpha, right, is the z-score such that the area under the standard normal curve to the right of z alpha is alpha. And so here's a problem. It says find the value of z sub 0.12. So that's the top 10%. We need to find the z-score that corresponds to the top 10%. And so we're using the standard normal distribution, which means the mean is 0 and the deviation is 1. Here, it would just be 0.9. And in fact, by default, we just do, let's change my calculator here. If I do second distribute and go to 3 and just put in 0.10, I'm done. I get it. There it is, negative 1.28. And that it's understood that we're going the area to the left. Now, top 10%, that's going to be 0.9, which is 1.28. So it's pretty nice that we can do it using inverse norm. So here is the 7.4 normal approximation to the binomial probability distribution, and that's the main objective here. So the criteria for a binomial probability experiment here. If all of these things are true, we will have a binomial probability experiment. So the experiment is performed in independent trials. Each repetition of the experiment is called a trial, and independence means that the outcome of one trial will not affect the outcome of the other. For each trial, there are two mutually exclusive outcomes, success or failure, and the probability of success P is the same for each trial of the experiment. And we also have here that for fixed P, as the number of trials in a binomial experiment increases, the probability distribution of the random variable x becomes more nearly symmetrical and bell-shaped. So as a rule of thumb, if n times p times 1 minus p is greater than 10 or equal to 10, the probability distribution will be approximately symmetric and bell-shaped. So the normal approximation to the binomial probability distribution is once this holds, x is approximately normal, the mean will be n times p, and the standard deviation will be the square root of n times p times 1 minus p. Alright, and so here the figure shows a graph of the probability distribution for a binomial random variable, and we get that the mean is 20 and the standard deviation is the square root of 10. So to approximate the probability of a specific value, such as like P of 18, we find the area under the curve from x is 17.5 to x is 18.5. We add or subtract 0.5 from x equals 18 as a correction for continuity because we are using a continuous density function to approximate the probability of a discrete random variable. So to approximate x is less than 18, compute the area under the curve for 18.5. To approximate x is greater than 18, we compute the probability of x is greater than 17.5. And so here's what's happening. As you can see, the exact value we would get, minus 0.5 plus 0.5. We would use that normal distribution, but we're going to tack on that extra 5, 5/10, extra half. Same thing there. And whenever we need to find the proportion between A and B, we will subtract 0.5 and add 0.5 respectively. So here is a question. It says, according to the American Red Cross, 7% of people in the U.S. have blood type O. What is the probability that in a simple random sample of 500 people in the U.S., fewer than 30 have blood type O? So first we have to verify that it is a binomial experiment. Each of the 500 trials are independent, and the probability of success is 0.05. Also, we need to verify that n times p times 1 minus p is greater than 10, and we see that it is. So now we're going to use the normal distribution to approximate the binomial distribution. We needed to find the probability that fewer than 30 people in the have a type O. So what we do is get the mean and the deviation, and now we're going to calculate it. It's going to be from 29.5 all the way down. So our lower bound will be some negative number, some, like negative 10, negative 100. Our upper bound will be 29.5, our mean 35, and our standard deviation would be what we got it to be. Now, whenever you're calculating the z-score, that's when you're going to use a table. You want to use the table because the table is reported in z-scores. So for table V, you can use table V, You just have to look up, negative 0.96. All right, and now here it says using the binomial CDF, we find the exact probability is 0.1678. The approximate result was close. Here's another problem. It says according to the Gallup organization, 65% of adult Americans are in favor of the death penalty for individuals convicted of murder. Erica selects a random sample of 1,000 adult Americans in Will County, Illinois, and finds that 630 of them are in favor of the death penalty for individuals convicted of murder. Assuming that 65% of adult Americans um, are in favor, what is the probability of obtaining a random sample of no more than 630? Alright, so we're dealing with a binomial experiment, and we check that n times p times the q, which is 1 minus p, is greater than 10. And now what we're going to do is find the probability x is less than or equal to 630. We need the mean and deviation. And now we will use the table. We can convert our z-score, but it's probably best to use technology. But what they're going to do is take 630 and convert it into a z-score. Because the normal distribution table doesn't change. It's the numbers that change. So if you standardize it, then we're referring to the same thing every time. Alright. Alright, we're going to take a look at some of the homework problems from Chapter 7. So let's take a look at 7.1 here. Just 15 questions. Which of the following is properties of the normal curve? That makes sense. Determine whether the graph can represent a normal curve. You saw the problem with that one. We had some negative values in there. This problem looks similar to the ones that we did. The graph to the right is a uniform probability density function for a friend who is x minutes late. Find the probability that the friend is between 5 to 10 minutes late. Yeah, there's a problem that we've done. So between 5 and 10, that's actually, the difference is 5, and the height is 1 over 30, so it's 1/6, or 0.667. 5 over 30 for part A. Between 5 and 10 minutes late, 5 times 30. Alright. It's actually 0.333. Let's see, 1/6. Oh, if we do 1 divided by 6, let's get the right amount for that. 0.1667. Okay, that's right. Alright. And now, if there's a 30% probability, find how long it's going to take him. It's a good question. Well, first we just have to figure out how far out in order to get 0.3, really. And in order to get 0.3, it seems to me we'd have to get 0.3 is equivalent to 3/10. It seems like 6 minutes, maybe. All right, let's do some math on that. We got 30% is 0.3, and one 30th .033 divided by I guess we need 0.3, so I'm gonna take 0.3 divided by 1/30th. And that's 9. Alright, well, let's keep going. I think it looks pretty straightforward there. Not bad, not bad. The figure to the right represents the normal curve. The area to the left of x is 250 is 0.15. Provide 2 interpretations of this. Well, the proportion of human pregnancies that last more than blank days is .1587. Alright, well, let's take a look at 7.2. We have a little bit more questions here. 7.2 is a little bit more important. You really got to be good at 7.2. The area to the right of z, this. Well, if we're talking about the area to the right, this would be our lower bound. And then our upper bound would be, so we're going to do normal CDF. Negative 0.75. And then some really large number like 100. And we get 0.7733 or 0.7734. The area to the right of z. So we'd have to put in a very tiny number, and then our lower bound would be negative 0.55, and our upper bound would be a very large number. So we would just change, instead of negative 0.75, we would put in negative 0.55. So we do each one of those. It's not too bad. Let's move on. Find the z-score that corresponds to the area under the curve to the right. Well, inverse norm only works for area to the left. So the area to the right is 15%. So what we'd have to do for inverse norm is put in the area to the left is 0.85. And we get 1.04. And we got it right. Alright, Z sub alpha, this is the top 7%. We're looking for the Z-score that corresponds to the top 7% there. Let's take a look at section 7.4. Yeah, this isn't too bad. Basically, they're saying we can approximate the binomial problems with the normal CDF one and get pretty accurate. All the conditions will have to be met in order to do that. Yeah, these problems are just very basic. There's no sense in overcomplicating this. I mean, we can just basically use the probability distribution. I mean, we can just go straight in here and get it done that way. We don't have to approximate. We just go straight in, second distribute, and then go in the binomial PDF, and we're going to put in the trials 72, probability 0.75, and then the x value, which is 50, and you get 0.0577. And there you just get it done that way. But you do, okay, so in order to answer this question, you got to double back and make sure that n times p times 1 minus p, which is 0.25, is greater than 10. And you should be good to go. Alright, we're going to end this video here. And if you have any additional questions, reach out and we can get them answered soon. Bye.